Our good friend resonance and inductive effects and electronegativity, all those things come into play. Just like we've talked about previously, we're just going to apply it to a different type of compound now. And then tautomerization. So again, you've heard about tautomerization, but we're going to talk a lot more about it today. So we really only have these two learning objectives. Explain pKa trends for protons alpha to a carbonyl. That's one carbon next to a carbonyl. And then the 4 Ps of keto-enol tautomerization. So let's start with our first learning objective. So this is the new chapter, 21A. Let's explain our pKa trends. Protons alpha to a carbonyl. To section 21.1. Okay, so if we have some generic molecule, like so, that has a carbonyl in it. So now this X could be like the X we talked about from last chapter. So it could be any carboxylic acid derivative, but it could actually also be a hydrogen or a carbon-based substituent to make it an aldehyde or a ketone. So any compound that has a carbonyl in it could do this. So the position next to the carbonyl, not the carbonyl carbon itself, but the carbon next to it is called the alpha carbon. And oops, go back. The proton on that position is called the alpha proton. Okay, so this is our alpha proton. It is much more acidic than a normal CH bond. So we normally don't think about carbon-hydrogen bonds as, being acidic, like you can pull off that proton. And that's because we're normally talking about alkanes. So if we just give an example here. So here's ethane. So this is an alkane. I've highlighted one of those protons in red. So that's the proton we'll be talking about. So the pKa of an alkane CH is about 50. That's super high, super high. That's really, really, really hard to pull off. And why is that? Well, if we look at what the conjugate base is, we would have CH3, CH2, and then that carbon would have a lone pair and a negative charge on it. So carbon with a negative charge on it is like not very stable. And there are no hetero atoms, there's no resonance, there's no nothing, right? So like this is not stabilized. Therefore, the conjugate base is not stabilized. The pKa of that proton is super high. So this is not acidic, essentially. On the other end of the spectrum, we talked about carboxylic acids, right? Where we had the acidic proton is on the oxygen. So the pKa of acetic acid was 4.7, so much, much more acidic. And the reason for that was because we had our conjugate base, which looked like this. And we stabilized this for a variety of reasons. First, negative charge is on oxygen, which is an electronegative atom, definitely happier than carbon. We also have the inductive effect, right? So that carbonyl is an electron withdrawing group. So through the bond, it's pulling electron density away, thus spreading it out and making it happier. And we also have resonance. Where we actually, through resonance, spread that negative charge to the other oxygen. And so we have resonance, induction, and electronegative atom. So lots of reasons why that carboxylate was very stabilized. Okay, so now we're talking about something in the middle. So it's not as acidic as a carboxylic acid, but it's much more acidic than an alkane. So if I take acetone as an example, so just a basic ketone here, I can highlight one of these alpha protons, right? So this is alpha to a carbonyl. The pKa of acetone is 19.2. So it's not 4.7, right? It's not as acidic as a carboxylic acid, but it's definitely not 50, right? So we're kind of somewhere in the middle, right? So let's think about why that is. Let's draw our conjugate base. So if I were to pull off one of those protons, I still have two more here. And I could put a lone pair and a negative charge, right, in that alpha position. So similar to the carboxylic acid, we have that electron withdrawing group kind of right next to it. So inductively, it is pulling some electron density away. But more importantly, we have resonance. So just like in the carboxylate example, we can push that lone pair towards the carbonyl and then break the double bond, put that negative charge on oxygen. So let's draw what our resonance structure looks like. So this looks a lot happier, right? Now we have that negative charge on the oxygen, which is better because oxygen is that electronegative atom. And in general, resonance stabilization is good. And so here we also have that resonance and induction. And a little bit of that electronegative atom, but only in one of the resonance structures, not both. So both of these resonance structures are valid. I will say that you should get in the habit of drawing it this way, because that is the more stable form, putting the negative charge on the oxygen instead of the carbon. Okay, so this is the topic of this chapter, essentially, is using this as our nucleophile. And I understand that that looks very strange, okay? The whole chapter is essentially this, which is called an enolate, we'll get there in a second, is a nucleophile. And nothing has changed throughout the entire semester. We're still going to be doing nucleophile, attacks electrophile, break the weakest bond. But a lot of students have a really hard time with this chapter because this nucleophile looks really weird. And I get it, it looks really weird. I am with you on that. But I promise you that, like, reactivity-wise, it's not actually that different. So as soon as you get comfortable with how this nucleophile reacts, it's very, very similar to everything we've learned, okay? So try to keep that in mind. It's just a weird looking nucleophile, but it's just a nucleophile, okay? Just like everything else we've learned. Okay, so let's draw out our entire sort of acid-base equilibrium here. So if we have whatever our X group is here, we have an alpha proton in the presence of some base. We're going to deprotonate that alpha proton. And we have two resonance structures, one where our negative charge is on the carbon, and the more stable one, which is where our negative charge is on our oxygen. So, and then our base has taken up our proton. So the two resonance structures in the brackets together, that is called the enolate. Right? Again, ate, ATE means negatively charged. So enolate means that it has a negative charge. And so we are going to be talking about the pKa trends of various alpha protons to make enolate nucleophiles. All right, so let's talk about our pKa trends. Okay, so there are kind of two factors that we have to take into account. The first is how electron withdrawing is that adjacent carbonyl. They're all going to be electron withdrawing, but how electron withdrawing? Can we compare them to each other? So let's start with an aldehyde. right? Or our X equals H in this case. Okay, we're always talking about the pKa of the red proton. Okay, so here's our aldehyde. So remember, carbonyls are always going to be electron withdrawing because we do have this resonance form where we just pull the electron density away from that carbonyl carbon to make a positive charge. This carbon does not have an octet, so it's not as high of a contributor, but it is a contributor. So that's why this carbon right here is positively charged, right? So if we look at it in our kind of more traditional form, we say that it has a delta positive charge, right? So this is kind of what I'm thinking about when I'm saying that our carbonyl is inductively withdrawing, right? So we are pulling that electron density. Remember those little inductive arrows? We're pulling that electron density away from that carbon. So the pKa of an aldehyde is 16, or for this aldehyde is 16.7. Okay. So now let's compare that to a ketone. Okay, so now again, acetones, we have CH3. We're still talking about this alpha proton over here. So the carbonyl is still pulling electron density away, right? But on the other side of the carbonyl, we have a methyl instead of a hydrogen, right? And alkyl groups are very slightly donating. And so that alkyl group is actually pushing electron density towards the carbonyl, which means that this carbon right here is less delta positive than it was in the aldehyde case. So if it's less delta positive, it doesn't have as much electron withdrawing ability. It still does, but just not as much. So therefore, it shouldn't be pulling as much electron density away, which is reflected in the pKa going up to 19.1. Okay, so this is an inductive argument. It's not as electron withdrawing, therefore, the proton is not as acidic because we're not going to stabilize the conjugate base as much as we would in the aldehyde case. Okay, I know that's a little bit harder to think about. The same thing we can think about for esters. So if we have ester, strangely, yeah. So we have an ester, still talking about this alpha proton right here. That oxygen on the ester right here can actually fully resonantly donate towards that central carbon. So that means that this carbon is much less delta positive. So again, it still is electron withdrawing, just not as much. Therefore, the pKa should go up again, and it does. This is 25.6. So if comparing an aldehyde to a ketone to an ester, the aldehyde alpha proton is the most acidic, then ketones, then esters. So it all has to do with how electron withdrawing is that carbonyl. Okay? Questions on that? I know that that's a little bit of a hard concept. It's all about the stability of that conjugate base, as always, right? Anytime we talk about pKa's, that's what we're talking about. Okay? So that's our first kind of criterion that we're thinking about. The second one I think is much easier. The second one is how many carbonyls are there? Okay. So let's start with two esters, for example. Okay, we have two esters. This proton right here is alpha to the left carbonyl and also alpha to the right carbonyl. And the pKa of this compound is 13. So this is 2 esters. So compared to a single ester, which was 25.6, right? We're way more stable than that, right? Because now we have 2 different groups that are stabilizing our conjugate base. We can also put those 2 things together. So if we compare 2 esters to 2 ketones, so again, that proton is alpha to each of the carbonyls. We've got 2 ketones. That should be even lower, which it is. The pKa of this is 9. So these are compounding effects, right? So you have to take both into account. How many carbonyls are there? That's the biggest effect, actually. And then what are the carbonyls? Are they aldehydes? Are they ketones? Are they esters? Like, you have to take both of those things into account. So these types of compounds are known as beta dicarbonyl derivatives. So that's kind of the generic term. And again, the reason for that is if I'm doing it in relation to, say, the left carbonyl, the alpha position is where the proton is, and the beta position is where the other carbonyl is. And so I could do that for any of these, alpha, beta, right? So again, let's explicitly state why that is. So regardless of what groups you have here in the R position, once we deprotonate that alpha proton, right, we can draw this resonance structure with the lone pair in between the 2. So we can then draw, pushing this lone pair, say, to the right. Like so. Or we can draw it all the way on the other side, where I can push my electron density all the way to the left. So our good friend resonance never goes away. Very important. So in this case, now we have more resonance stabilization. If we have more resonance stabilization, it's a more stable conjugate base. Therefore, it's a more acidic proton. Okay. So the rationale that we've been using for every pKa trend that we've learned the entire semester is the same here, right? It's just that it looks a little bit different because what is causing that additional stabilization is slightly different, but it's the same principles. Questions? Let's do a timing question to see if that's making sense. All right, I'm giving you 4 compounds here. I'm asking you, which compound would you predict to have the lowest pKa of the red proton? So the red hydrogen here. So again, there's lots of different ways we could ask this question, right? So make sure you read questions carefully. So in this case, it's asking for the lowest pKa. We could have asked for the highest pKa. We could have asked for the more acidic or the least acidic or the most stable conjugate base or the less stable conjugate base. All of those questions are asking the same thing, okay? So in this case, the lowest pKa. So feel free to chat with your neighbors, see if you are getting the same answer. Maybe 10 more seconds to get your answers in. All right, let's see what we got. Okay, all right. So most people are getting it. A is the correct answer, but the other answers are pretty spread. So there's some confusion here, which is not surprising. Again, this is a very challenging concept. Okay, let's talk through this real quick to make sure we're all on the same page. Okay, so we had 4 options here. We had a diketone, we had an aldehyde, and an alcohol, we had a ketone and an ester, and then we had 2 aldehydes. Okay, we're going to highlight the red proton in all cases, like so. Okay, so the correct answer is this one. So this has our lowest pKa. We have 2 ketones alpha to that proton. So let's talk about why the other ones are not it. So on the next one, that is an alcohol. That's not a carbonyl. So it can't stabilize our conjugate base through resonance, right? So how we drew these 2 resonance structures up here, an alcohol can't do that, right? So it's not just the presence of an oxygen or a heteroatom or something. It's like you actually need a carbonyl. So that one doesn't work. The next one, this is an ester, right? And we said that so we have 1 ester and 1 ketone. And we said that esters are not as good as ketones as stabilizing a conjugate base. Therefore, it's not going to be as good as 2 ketones. Okay. And then the last one, yes, there are 2 carbonyls, and yes, they are aldehydes, but these 2 things are not beta to each other, right? So there's really only 1 aldehyde alpha to the proton. That guy can't stabilize through resonance. So it really matters where the positions of those carbonyls are, right? So in this case, they are right next to, right, the alpha proton here, whereas this one, it's 1 carbon away, which means that you can't do that resonance anymore. Yes?
Hypothetically, if the double bonded O on the D moved over this one, so it would be beta, would that?
Yes, great question. So if instead of a diketone, we had hydrogen and hydrogen here, yes, that would be the most acidic. Yeah, because aldehydes are better at stabilizing than ketones. Yeah, great question. Any other questions on this? So it's really those 2 factors are what you're looking at. Number of carbonyls available to resonantly stabilize, and then how electron withdrawing are those carbonyls. Okay? All right. 2 random asides about this. First, pKa's matter. So the pKa's of the base that you use also matters. Okay? So we're going to keep using acetone as our example, just for funsies. So again, our pKa of acetone is about 20, 19 and change, but about 20. If we were to use sodium hydroxide, right? Classic base, we use that a lot. You can do this. I'm going to draw my equilibrium arrows suggestively. We will form an enolate. Looks like this. We have our sodium counterion, and then we have our water as our byproduct here. Okay, so here's our enolate. And our water has a pKa of 15.7. So what does that mean? 15.7 is a lower number. It is more acidic, right? So that means that it is actually more favorable for the enolate to deprotonate water and to go back over here. So it can happen, just not a lot. So at equilibrium, we have less than 1% of our enolate at equilibrium. Okay. Now, 1% can be enough to do chemistry. So you're still going to see this, but it does cause problems in some cases. Okay. So you just have to be aware that if you're using sodium hydroxide to form your enolate, you're not just like forming a full enolate and then going on and doing things. That's not how it works. So on the other hand, if you were to use, a stronger base, so say LDA, so LDA is lithium diisopropyl amide. So negatively charged nitrogen, right? We've talked about how negatively charged nitrogen is very not happy. So it's super reactive. Okay, so this is called LDA. Lithium diisopropyl amide. Okay, not to be confused with an amide, even though it's spelt the same. I'm sorry, I know it's annoying, it's confusing. But AMIDE also means negatively charged nitrogen, which is what it means in this case. So here, okay, we have our pKa of about 20 on this side. So now our equilibrium arrows are going to be the other direction. We form the same enolate. Now we have a lithium counterion. And now our byproduct is diisopropyl amine. And this diisopropyl amine has a pKa of about 40. So that's a higher number, right? Amines are not acidic, they are basic. So it really, really, really doesn't want to get rid of that proton. So essentially, we have 100% enolate formation. So we would consider this an irreversible deprotonation. So that's going to come up later when you need to fully form an enolate before doing the next step. Yes. On the conjugate. Oh, yes. Sorry. These groups are called isopropyls, right? And so IPR means isopropyl, and there are two of them. Yep. Other questions? Okay. Yes. Yep. So the pKa of this is lower than the pKa of this, right? So that means that water is more acidic than your ketone. So it is more likely to be sitting on the left side of this equilibrium than the right side. Yeah. So you can still form it. You're just forming a very tiny little amount of it. Yep. Okay. So that's caveat number one. This is going to come back later, but I just wanted to introduce the concept now. pKa's matter. So thinking about our pKa's is really important. The second thing that we need to remember is that esters can do other reactions. So we just spent a whole chapter talking about carboxylic acid derivatives and that esters can like do things, right? So if instead of acetone, we had an ester here, okay, we're still talking about the red proton. If we were to mix this with sodium hydroxide, you might want it, desired, to form the enolate. Okay, you might want that to happen, but that does not happen. Instead, we have to remind ourselves that esters can do other reactions. So we learned that if you mix esters and sodium hydroxide, instead, your actual reaction will be saponification. And so your alpha proton doesn't react at all. You do saponification instead, which is the hydrolysis of esters to the carboxylate under basic conditions. Okay, so you got to remember that that can happen. So instead, how do we get around this problem? So instead, you're going to use an OR minus that matches the ester. So in this example, that would be sodium ethoxide. Okay, so this ethoxide should match the X on your ester. Okay, so your base, instead of being OH, because that's going to form this carboxylate and then you're stuck, if you use sodium ethoxide, even if it tries to do nucleophilic acyl substitution, you get the same thing back, so it doesn't matter. Right, so that's how you get around it. Is anytime you're using an ester, make sure that your base matches the ester. Questions? Okay, that's pKa. Alpha to a carbonyl is acidic, much more acidic than normal CH bonds. We make enolates. We're going to use enolates as the nucleophile this whole chapter. Okay, all right, let's talk about tautomerization. So our other learning objective is the 4 P's for keto enol tautomerization. So this was introduced in 9.11 and now kind of going more in depth in 21.6. Okay, so our keto form is the one we normally see, right? Something like this. Could be an aldehyde as well, but it's normally, people call it keto enol tautomerization. So ketone. Okay, there's going to be some equilibrium. It actually favors this direction to our enol form. Okay, again, ene, alkene, all, alcohol. We have an alkene and an alcohol. It's an enol. So the ketone is usually favored. Not always, but usually. We've also talked about a lot of reactions with ketones. We know that ketones are electrophiles. This is our electrophilic form. Whereas our enol is a nucleophilic form. So there are times when you're going to want one or the other, depending on whether you need this to act as a nucleophile or an electrophile. So this process is called keto enol tautomerization. Okay, this process can be either acid or base catalyzed. Notice that on both sides of this equilibrium, they are both neutral molecules. So this is not an enolate. It's not negatively charged. It's the enol, which is the neutral form. And then again, you want to consider, are you looking for nucleophilic or electrophilic reactivity? Where your nucleophilic means that you want the enol form, and electrophilic means you want the keto form. Okay? Because they're two different forms of the same molecule, but they have very different reactivities. So we're going to go through the mechanism, both acid and base catalyzed in both directions. Luckily, it's 2 proton transfers every time. That's it. 2 proton transfers. It's just a matter of what's getting deprotonated or protonated at various times. So let's start with the mechanism under acidic conditions. We'll go from keto to enol. And we'll do a specific example. How about? So here's an aldehyde. We have 1 alpha proton. Acidic conditions, we want positive charges. So we better protonate first. So just like every other reaction that we talked about last chapter, where you need to protonate first under acidic conditions, same thing here. So we'll just use a generic H3O plus acid. We're going to protonate the carbonyl, because it's the most basic site of our molecule. So positive charge in acidic conditions, that's good. Then we have water. So 1 proton transfer to protonate. Second proton transfer, we deprotonate that alpha position. That carbon-hydrogen bond breaks, and we form our enolate. So we push that electron density into that carbon-carbon bond to form our ene, right, our alkene. And then we break the carbon-oxygen double bond to quench the positive charge. So now we have a carbon-carbon double bond. We have our OH, and we regenerated our acid catalyst. Okay, so this is catalytic. So you only need a little bit to get this to go. Okay? But again, it's all equilibrium, right? So now that's when we have to think about the pKa's. So the ketone form is normally favored, but you can make both. All right, let's do the reverse. So enol to keto form. We're going to start with the product that we just made. So start with the enol. Okay. We're under acidic conditions. We better protonate first. Okay, so here is the weird arrow pushing. Okay, this is the thing that confuses everybody in this chapter, but I promise it's always the same. When you're using an enol or an enolate as a nucleophile, the arrow pushing looks like this. You take one of the lone pairs from the oxygen, you push it down to reform the carbonyl, and then you use the carbon-carbon double bond electrons to attack whatever you're attacking. So in this case, the proton. And then we break that bond. Okay, push down to reform a carbonyl. Carbon-carbon double bond goes out and attacks things. And then we had to break the proton-oxygen bond. It's the exact reverse. The exact reverse of this step is right here. It has to be exactly the same in reverse. So what does that get us? That gets us to here. Our red proton is again in that alpha position. We have our water. Okay, positive charges, acidic media, good. We did our protonation. Now we just have to do our deprotonation. Water pulls off that proton, quenches the positive charge. And we regenerated our catalyst again. It's 2 proton transfers. That's it. 2 proton transfers. Okay. Under acidic media, you better protonate first and then deprotonate, because you want positive charges. Questions on acidic conditions? Okay, basic conditions. I bet you can guess that we're going to deprotonate first and then protonate. So now we're going to do mechanism under basic conditions. Again, we'll start keto to enol. Use the exact same sample aldehyde with 1 alpha proton. Okay, now we're under basic conditions. So we're going to use sodium hydroxide. So under basic conditions, we want negative charges, not positive charges. So we're not going to protonate first. We're going to deprotonate first. What are we going to deprotonate? The acidic proton, the alpha proton, the one that we've been talking about this whole time. So base grabs that acidic proton, carbon-hydrogen bond breaks, form the carbon-carbon double bond, break the carbon-oxygen double bond, dump the electron density on oxygen. Now we have a negative charge, which is fine because we're under basic conditions. Okay, so that was our deprotonation. Now we need to protonate. We better protonate this negatively charged thing, right? So that is oxygen is just going to grab the proton. Oops, sorry, that should be red. Let's track our atoms. There we go. Okay, and we regenerated our sodium hydroxide. So again, this is catalytic. Yet again, it's 2 proton transfers. We just did them in the opposite order. We did deprotonation followed by protonation. Okay, the hard part is knowing what gets protonated or what gets deprotonated at which time. Got one more. Let's do the reverse. We'll go from the enol to the keto, starting with the compound that we just made. Okay, so there's our enol form. We still have base around. So we're under basic conditions. We better deprotonate first. What's the most acidic proton? The enol proton. So this is going to pull off that proton to form our enolate. Here's our O minus. Sodium is our counter ion. We formed water. Okay. So again, here, this is the weird arrow pushing. This is the arrow pushing that I want you to practice and get comfortable with, because all of next week, it's using this arrow pushing for a bunch of different reactions, okay? Lone pair on the oxygen pushes down to reform the carbonyl. Carbon-carbon double bond, those 2 electrons are the thing that go out and attack things. And you end up at putting that proton back at the alpha position. So that is the interesting sort of different arrow pushing that is going to be used throughout this entire chapter. And we regenerated our base. Questions? So 2 mechanisms, 2 orders, but it's just 2 proton transfers. That's all it is. You just got to think about which direction is the proton moving. Okay. In the last couple minutes, I want to do one last chime-in question to see if you are thinking about this enol form. Is kind of weird, right? Which is the nucleophilic atom in the enol form? Because this is really important for reactivity, right? So which is the nucleophilic atom? Is it the oxygen? Is it what was the carbonyl carbon? 3 is the alpha carbon, 4 is the one next to it. So which one is the nucleophilic atom that's going to end up being attached to whatever your electrophile is? Okay, maybe 10 more seconds to get your answers in. Finish on time. All right, let's see what we got. Okay, yes. So carbon number 3 is correct. The alpha carbon, that's the one that's going to end up attached to things, right? I see why people think it's number 2 though, right? Because we're using that carbon-carbon double bond. But you got to make sure that you're thinking about the alpha position is where the reaction is happening. Okay, great job. I'll see you next week. Please practice this arrow pushing. It will make next week really easy.